Hello students, welcome to the topic on line coding. So before getting into line coding, you need to understand what you mean by encoding. So we know in computer communication, the data will be transmitted in the form of zeros and ones. So these zeros and ones, when it needs to be transmitted via the medium, it needs to be converted into some form of electrical signals. So we know the signals will be basically represented as a positive and negative voltage. So in this line coding, there are various types of line coding technique, and these signals could be represented in various forms. So in this line coding, we are basically going to see the various types of line coding. So line coding basically, there are various techniques like unipolar encoding, polar encoding, bipolar encoding, multi-level encoding, and multi-transition encoding. So in unipolar encoding, we are basically going to focus on non-return to zero, and in polar technique, we are going to see what do you mean by non-return to zero, and biphase. So in biphase, we are having two types. One is called as Manchester and differential Manchester encoding. So in bipolar, we are having techniques like AMI and pseudo ternary. And in multi-level, we are having 2B1Q technique, 8B60 technique, and also 4D PAM5 technique. In multi-transition, we are going to see about MLT3. So this PPT will be basically focusing on unipolar and polar technique only. So first let us get into unipolar. So unipolar technique, all the signals will be represented on one side of the time axis, either it could be above or below. So for the bit position 1, we are going to represent it in unipolar as a positive voltage, and 0 is going to represent it as a negative voltage. Non-return to 0 is an example of a unipolar technique where the signal will not return to 0 at the middle of the bit position. Okay, so but this scheme is prone to baseline wandering and DC component. It is not having synchronization or any error detection techniques. It is simple to implement, but it is costly in terms of power consumption. So coming to unipolar encoding. So here we could see the diagrammatic representation of unipolar encoding, where we are having y-axis as amplitude and in x-axis we are having the time. So there is a bit representation like example as 0, 1, 0, 0, 111, 0. So we know in the previous slide we have read that 0 is represented as a negative voltage. So here you could see 0 is drawn as a negative voltage, 1 is represented as a positive voltage, again 0 is represented as a negative voltage. So since in this diagram there are two zeros, you could draw this 0 continuously. Again there is 111. So it is a positive voltage, so you can draw it as a straight line. And again 0 is a negative voltage. So this is how you convert the bits into signals. Okay, so this is basically called as your unipolar encoding, and let us get into the next type of technique. So coming to the types of polar encoding, we are going to see polar encoding is basically classified into non-return to zero, return to zero, and biphase encoding. And in non-return to zero, it is basically classified as non-return to zero L. L stands for level, and non-return to zero I. I stands for your inversion. Likewise, we are going to see return to zero. And then in biphase, it is having two flavors. One is called as your Manchester and the other one is called as your differential Manchester encoding. So first let us get into non-return to zero. So in non-return to zero, we could represent voltages on both sides of the time axis. Whereas in unipolar, what we have seen? We have seen only it is lying on the upper axis, okay, which is nothing but the top of the x-axis. Okay, now we are going to see polar non-return to zero scheme. It could be implemented with two voltages. So we could represent 0 as a positive voltage and 1 as a negative voltage. So there are two versions of non-return to 0. Basically it is called as level. Level means either it could represent one symbol for a positive voltage, and the other symbol will be using a negative voltage. Likewise, non-return to zero inversion. So inversion means the lack or change in the polarity will determine the value of the symbol. So wherever we are getting a 1, the symbol will be inverted, and wherever we are getting 0, the symbol will not be inverted. So we'll see in the diagrammatic representation, so that we'll see how exactly we are converting the bits into signals. So this is a diagrammatic representation of non-return to 0 L and non-return to 0 I. So here again we are drawing it as a x and y axis. So we are having amplitude in the y axis, and in the x axis it is represented on the time. So first we'll see the non-return to 0 L. L stands for level. So level means you have only two levels, positive and negative voltage. So for example, in this diagram we are having bit position like 0, 1, 0, 0 and triple 1, 0. So a 0 is represented as a positive voltage, 1 is represented as a negative voltage. Again we are having 0, it is a positive voltage. Okay, then it will come to 0. Again it is a triple 1. So it is represented as a negative voltage, it will come back to 0. Again 0 means it's a positive voltage. So this is how you convert the bits in non-return to 0 level. Okay, so coming to the bottom diagram, so here we can see the diagrammatic representation of non-return to 0 I. I stands for inversion. So coming to the bit positions, so first we'll see if the next bit is 0, there is no inversion in the signal, but whereas the next bit is 1, there is inversion in the signal. So let us look at the example so that we can understand how we are converting the bits to signals. So first is 0. So when the next bit is 0, there is no inversion. A 0 is represented as a positive voltage over here. Okay. Then next bit is 1. Okay. So whenever there is a 1, there will be an inversion. Okay. So here you could see there is an inversion. It is coming to the lower voltage. Okay. Then again 0. It will be continued to remain in the same. Okay. Again in the lower axis. Again the next bit is 0. It will be again in the lower axis only. Now the next bit is 1. So here you could see the next bit is 1. So there is an inversion. So from the negative axis it will move to the positive. Okay, again the next bit is 1. So again there will be an inversion. So from the positive it will come down to negative. So the next bit is 1. Again it will be converted to positive. Next bit is 0. So it will try to remain in the same level. Okay, so this is how you can do the conversion of the bits in non-return to 0 I. So here you could see the bandwidth representation, and also the S average is basically here n divided by 2. So coming to the next technique, which is called as polar, which is called as return to zero. So a return to zero scheme will be basically using three voltage levels. So you could see it is using a positive, zero and negative voltage. So here each symbol will be having a transition in the middle. Either it could be from high to low, high to zero, or from lower to zero. So this scheme has more signal transitions, that is nothing but it is using two per symbol, and therefore it requires wider bandwidth. So here also we are not having no DC component or baseline monitoring, and it is not synchronized. It is more complex as it is using 3 voltage level, and it is not having any error detection capabilities. So coming to the diagrammatic representation of polar return to zero. So here you could see, for example, this is also again drawn as in the y-axis we are having amplitude, and in the x-axis we are having time. So for example, they have represented as the bits as 0, 1, 0, 0, 1. Okay, so what we have seen for 0, so for 0 it could be either from high to 0 or low to 0. So here for 0 it is low to 0, and they have taken 1 as high to 0. Again 0 means it is low to 0. Again it is 0 means low to 0. 1 is represented as high to 0. Then we will be connecting the intermediate lines. So this is how you convert it in terms of your return to 0 scheme. So here you could see how the bandwidth is represented, and here the S average is basically N. So coming to the next technique is called as polar, and in polar here we are having two types of biphase techniques. So one is called as your Manchester, and the other one is called as your differential Manchester. And in Manchester encoding, so it is basically a combination of two flavors. One is we are having non-return to 0 L. L stands for your level where it is having voltages. Okay, either it could be a positive or a negative voltage. Likewise in return to 0. Okay, and every symbol here will be having a level transition in the middle. Either it could be from high to low or from low to high, and it uses only two voltage levels in case of your Manchester encoding. So coming to the next type of technique is called as a differential Manchester encoding. So differential Manchester encoding, it is the combination of not return to 0 I stands for your inversion, and then it is the combination of return to 0 schemes too. So here every symbol will be having a level transition in the middle, but the level at the beginning of the symbol will be determined by the symbol value, and one symbol will be causing a level change, the other does not. So once we look at the example, we will understand how we could convert your bits into Manchester and differential Manchester technique. So now let us get into the diagrammatic representation of zeros and ones. So here in Manchester encoding, so again here we could see first we'll complete Manchester and then we'll go into differential Manchester. So for the bit position 0 in Manchester encoding, you represented as a high to low and 1 is represented as a low to high. So here there is a mid bit transition. So coming to the positions, so you can see 1 0 1 0 0 1 1. Here you could see the signal will be transitioning in the middle of the bit. So a 0 is represented as a high to low. 1 is represented as a low to high. Again 0 means high to low. 0 means high to low. 1 means low to high. Again 1 means low to high. So then you will be connecting, you will be interconnecting the remaining lines. Okay. So this is how you convert your bits into Manchester encoding. So coming to your differential Manchester encoding. So in differential Manchester encoding, we know it is a combination of non-return to 0 I and return to 0. So non-return to 0 I means we know it is an inversion. So whenever the next bit is 1, there will be no inversion. And when the next bit is 0, you could possibly see an inversion happening in your differential Manchester encoding. So here you could see the 0 actually based on the previous value only this inversion will happen. So 0 will be having two changes, like there will be a change from high to low and low to high. So two changes will happen for the value 0, but whereas 1 will be represented by only one change, either it's from high to low or low to high. That is a combination. Okay, so first is 0. So 0 you could see there is two change. So it is from high to low, again from low to high. Okay, then the next bit is 1. So whenever the next bit is 1, there will be no inversion. So no inversion means it will continue to be in the same level. Okay, so it will be in the same level and then it will be going down. Okay, so the next bit is 0. So whenever the next bit is 0, you could see there is an inversion happening. Okay, since it is in the lower voltage, then there is a there will be inversion happening. So it is from here you have to see it is uh, negative to positive, again positive to negative. There are two changes. Next bit is 0, again negative to positive, then positive to negative. Then the next bit is 1. So whenever there is 1, we know that there is no inversion. So it will be trying to be in the same bit position and then it will move up. So likewise the next bit is 1 means it will be in the same position and then there is a negative voltage. So it will move from positive to negative voltage. So this is how you can convert the bits in terms of your Manchester encoding. So here you could see the how it is represented in terms of your bandwidth. So here you could see the S average is basically N. Thank you.